Good morning. Let's begin. Today, lecture 27. We will do a run through of lecture 25 and 26 because those were both covered yesterday and we had a number of new concepts. Again, the idea is to put all these pieces together like the jigsaw puzzle and then see how they fit together. So, in the last lecture, if you were to sort of quickly run through the concepts, we talked about all pass functions, properties, all pass lattice, talked about certain qualities or characteristics of functions called boundedness, losslessness and the combination. We talked about factorization of polynomials. When you want to divide the zeros of a polynomial into two sets, maybe in those zeros inside the unit circle, those outside the unit circle, that is one type of factorization that you would like to do. Then also the all pass decomposition theorem, and somewhere along the line we talked about M band filters, mth band filters, what are their properties. We also talked about half band filter, and then we said that these pieces together will help us reach perfect reconstruction, which we did not reach yesterday, we will reach today. Okay, so by way of recap, here are some key points, maybe a good idea if you want to note them down, that way it will be a revision and also a reinforcement of what we have discussed in the last lectures. So, these are concepts covered in lectures 25, 26, not necessarily in the same order, but all the points are mentioned. One of the key elements or key tools that we are going to be using is the paraconjugation, where you conjugate the coefficients and replace z with z inverse. This is a very good definition that we want to keep for us. Now, the reason paraconjugation is very beneficial is because that is the analytic extension of conjugation on the unit circle. So, this is something we will use quite extensively, especially in today's lecture. This can be viewed as h tilde of z, h of z on the unit circle. Okay, that is an important element. Now, moving from this, this also tells us that the zeros are at reciprocal conjugate locations. So, if h of z not equal to 0, h tilde, this means that there is a z is equal to z naught, h tilde of z naught equal to 0 means that you have a 0 at 1 over z conjugate. Okay, so basically the reciprocal conjugate location is where the 0 will lie. So, that is where the 0 will lie. So, given this, we also said that the structure of an all pass function can be written in the form b of z divided by z power minus n b tilde of z. The z power minus n is only to give you a causal transfer function. This basically means that you will have a all pass because you are guaranteed that h a p e of j omega magnitude squared is equal to a constant for all values of omega, because the numerator is the conjugate of the denominator. We also have the maximum modulus theorem. So, this is the structure of all pass functions, and the maximum modulus theorem also plays a role whenever we work with. So, basically if h a p of z is a causal stable all pass, is a causal stable all pass function, then we can say the following: magnitude h a p of z equal to 1 on the unit circle, it is less than 1 for points outside the unit circle, greater than 1 for points less than inside the unit circle. Again, this we saw actually helped play a role. So, these are some concepts that we have worked with. Combine it with the all pass lattice, where we have the input output relationship given by equation 3. That is an important relationship, and we showed several interesting and important results from this. One of them was that if you choose Kn appropriately, then you get Gn minus 1 as a lower order all pass function if Gn of z is an all causal stable all pass, and Gn minus 1 is a lower order also causal and stable. So, those are that is a useful result. The other one is that you can actually carry this forward for the entire length of the basically for the based on the order of the filter, you will get that many stages, and you will basically get these coefficients kns. You can call them as coefficients of the all pass lattice, sometimes they are referred to as reflection coefficients, again depends on which background you are coming from. The KIs, the important thing to note is that if all the KIs are upper bounded by 1, that means they are strictly less than 1, then you are guaranteed that the transfer function that you have synthesized is a causal stable all pass function. Okay. And again, this is a useful result in the context of all pass. This also tells us that what are the properties an all pass function should satisfy. Okay, before we get to the all pass decomposition, let me just review a couple of other points. The notion of a bounded transfer function. We are going to be talking about boundedness. It is a very important concept. Basically that means that you do not have the frequency response suddenly shooting to some large value, it is bounded. And we also look at transfer functions where the bound is 1. So, which means that it is like a filter response which maximum response is upper bounded by 1. So, a bounded transfer function H e of j omega magnitude squared is less than or equal to 1 for all values of omega. That would be a good way to define the bound for a filter. Now, it becomes bounded real if all these coefficients, which are the impulse response, they are elements of the real value set. Basically, if you have those as not as complex numbers, but as real valued, and of course, you can have the lossless property, which is the same as energy preserving between the input and the output, and the all pass is one of those class of functions, and therefore, if you have LBR, that basically points to an all pass with real coefficients, Okay. That is an important observation. We also have another class of functions called power complementary transfer functions. This says that if I take the magnitude squares of these functions or filters, then they add up to 1. Okay, this is a very useful class, as you will see in today's lecture, because this is what actually solves the final problem of perfect reconstruction. Now, it is not necessarily limited to the 2-channel case. The general case says summation k equal to 0 to m minus 1 mod h k e of j omega magnitude squared equal to 1. You have a set of transfer functions which, and we made the following observation that if you have okay, when we come to that we will discuss. Basically, mth band filters give us a way to satisfy these types of conditions, but we will come to that in a minute. The other element that is very useful for us in today's discussion is the factorization. So, the factorization, how do you visualize the zeros of a polynomial, and how do you separate them into 2 sets. So, basically yesterday we showed that if you had a transfer function h of z, which can be written as a of z times b of z, this has n naught zeros inside the unit circle, inside mod z equal to 1. We are taking the case where there are no zeros on the unit circle. This has n1 zeros outside mod z equal to 1, and we have said that this can be written as h all pass h min of z times h all pass of z. Okay. Minimum is minimum phase, all pass is a causal stable all pass. This one has got the same order as the original transfer function. Okay, this one has got same order, or in other words same number of zeros, same order as h of z. This is a very convenient factorization, but more importantly just for you to think about that if I have zeros and I want to separate them out, that the process of separating zeros is the process of segregating factors. Okay. Factorization basically says find the zeros, but once you have found the zeros, how do you separate them, aggregate them, so that is a useful process. Okay. Now all pass decomposition theorem, again will not go through the details. Two nth order bounded real transfer functions, nth order bounded real transfer functions of the form p naught of z by d of z, p1 of z by d of z. P naught has got even symmetry, the coefficients have got even symmetry, P1 of z have got anti-symmetry. So therefore you have this relationship. We showed that if H naught and H1 are power complementary, then we can factorize them into this form. Okay. So I thought it would be helpful for us to go back and apply this to the two channel case. So if you remember the two channel case is this structure, please apply the all pass decomposition into that framework. So let us just spend a minute to do that. So the two channel maximally decimated filter bank, maximally decimated QMF bank. Okay, so keep that structure in mind. So what we have is that we have T of z, which is given by 1/2 of H naught of z f naught of z plus H1 of z f1 of z, and we have the A of z, which is the aliasing term, transfer function of the aliasing term. It is 1/2 of H naught of minus z f naught of z plus H1 of minus z f1 of z. Okay, again this is nothing new, basically from the earlier result. We then, if we impose the aliasing cancellation constraint, f naught of z is equal to H1 of minus z, f1 of z is equal to minus H naught of minus z. Okay. This is enough for us to guarantee that A of z equal to 0. So without loss of generality we can get rid of aliasing in a two channel case. Now the other condition that we imposed was the QMF condition. QMF condition, if you recall, was that the two filters are not independent but actually shifted versions of each other, H naught of minus z, and if we substitute this into the transfer function along with the aliasing cancellation constraint, then we get T of z equal to 1/2 H naught squared of z minus H1 squared of z, right. If you go through the substitutions, basically substitute the aliasing cancellation constraint and the QMF constraint, this is what we get, and this we can write as 1/2 H naught of z plus H1 of z into H naught of z minus H1 of z. If you go back and look at your all pass decomposition, add H naught and H1, you will get A naught of z. So this comes out to be A naught of z, this one comes out to be A1 of z, A1 of z. So the overall transfer function T of z is equal to 1/2 of A naught of z A1 of z, and This is a case where we have eliminated the aliasing, eliminated the magnitude distortion because the transfer function, but there is phase distortion which we have not done anything about. Okay. Is that okay? So this is different from when you did the polyphase decomposition and forced the polyphase components to be all pass function. This is a different case. This is a case where we did all pass decomposition of the filters themselves. Basically, you had a pair of power complementary filters. In the earlier decomposition, there was no power complementary part. You took the filter polyphase components and we tried to force them to be all pass components. Here is a case where you did the all pass decomposition, and as we mentioned, there is a class of filters that can be designed primarily in the context of elliptic filters, where you can enforce the power complementary property, and because you can enforce the order and the power complementary property, you can also get the all pass decomposition. So this is not just a theoretical exercise, this is quite a practical system that can be designed and implemented without too much of difficulty. Okay, but here is the task I want you to tell me now. So far, what are some of the concepts that we have seen in lectures 25 and 26? So if I were to write them down, so the concepts, again keep it like a jigsaw puzzle, the different pieces that the first one that we have seen is factorization and grouping of zeros. We saw that in the design of the all pass decomposition part. So basically you took the zeros of P0 plus P1, the zeros inside the unit circle, outside the unit circle, and then factored it and said this one goes into D of Z, the other one goes into D tilde of Z. So factorization and grouping of zeros, that is an important tool that we have leveraged in this section. Second, we have leveraged the notion of a minimum phase factor. That is one grouping where all the zeros are inside the unit circle. We have also leveraged paraconjugation. Paraconjugation says a zero inside the unit circle and its reciprocal conjugate both will produce the same magnitude response. Paraconjugation property also a useful part of this. And fourth concept that played a role in the all pass decomposition was the power complementary property. Okay. So these are the points to keep in mind as we move forward. Now comes the next element where we talked about the mth band filter or a Nyquist filter. Okay, so Nyquist filter, again we will not repeat the earlier discussion, but basically what we said was, if I look at the interpolation filter for a interpolation after upsampling by a factor of m, then the impulse response h of n comes out to be sin pi n divided by m by pi n over m, and using this we get the following result, that h of mn equal to 0 if n not equal to 0, equal to 1 if n equal to 0. Okay, so basically from the expression of the sinc function. So what we found was that only one non-zero sample was there for one of the polyphase components. So this is something that we leveraged. So this basically said that if I took the polyphase component E naught z power m, that as 1, then we have the following property of an mth band filter. An mth band filter by definition must satisfy the following condition: 1 over m summation k equal to 0 to m minus 1, h of z w m raised to the power k must be equal to 1. And it's we showed that a Nyquist filter will satisfy this property. Okay. So, but mth band is more general, it takes into account these types of filters that have this property. And we also mentioned that a special case is when m equal to 2, we call it a half band filter. half band, this is going to play a very important role today. This is 1/2 of h of z plus h of minus z equal to a constant equal to 1. We looked at a half band filter, basically took at the Nyquist filter with m equal to 2, and we came up with an interesting observation. The observation was that the length of the half band filter, because of the symmetry and every alternate sample being 0, was 4j plus 3, which means that if I shifted it to the right, made it causal, then the filter order will be 4j plus 2, which is even but not multiple of 4. Now, you may ask, is that significant? Actually, it turns out to be significant. Let us just look at it, even but not multiple of 4. Multiple of 4. Okay, so that's, again, these are all pieces of the puzzle. Then the last part where we stopped was this DFT filter bank. So basically, mth band filter, we said, satisfied this property if you had these shifted versions of the basic filter h naught of z, and it shifted in this form. We can write this, basically this should be W dagger. I think yesterday we made the correction, inverse same as W dagger with the scale factor. So basically we said that the filters, shifted filters, the DFT filter bank, they form a power complementary set if the polyphase components form a power complementary set. Now, you may say, well, I am not even sure where this is going to play a role, but this is a observation that we can make because if you look at what is the computation that we are doing, W dagger times W dagger is equal to m times I. So, the inner pair gets cancelled, you basically have a diagonal matrix. Gamma tilde of z times gamma of z also is equal to the identity matrix. So, basically that is how the proof works out. Okay, the next statement is probably the one that left people with a few questions, but again I want to emphasize that. So, the power complementary property says that hk of z, hk tilde hk, if I add them up, they should be a constant. Okay. Now, if I could have written g naught of z as h naught of z tilde times h naught, okay, if I can write it in this form, and g naught satisfied a mth band property. Mth band property basically says the shifted versions will add up to a constant. If I now substitute this factorization, I get a power complementary set. Okay. There are two assumptions being made. One is g naught is being factorized into this form, second one g naught satisfying the mth band property. If those two are satisfied, then I get a factorization. Now, how do I get g naught to be a factor of this kind? Because on the unit circle this means its magnitude squared. That is what we talked about, taking the 0 phase response and then shifting it up so that these individual zeros merge to become double zeros, and therefore you have a way to work with this. Let's pick it up from this point. We are interested in a half band filter. So let's focus in and make some statements about the half band filter. Half band filter. I want to design a linear phase half band filter. Okay. Now, basically we want to say that g naught dash e of j omega is a half band filter, which means its shifted version will add up to, and let us say that we have designed it in the following fashion, that there is equiripple in the pass band and the same magnitude ripple in the stop band also. So, the upper limit is 1 plus delta, 1 minus delta, this is plus delta and minus delta. Those are the limits or where the fluctuations are observed. Okay. Now, this is a 0 phase response. I have taken out the phase. So, this is a real valued function, but it can take positive and negative values. Now, if I define G naught E of j omega to be equal to G naught dash E of j omega plus delta. Okay. So, then what happens? This amplitude response shifts upwards, and now we have the response. Okay. So, the upper limit is 2 delta, okay, and the upper limit here also is 1 plus 2 delta, because everything got shifted, and the lower variation is at 1, everything got shifted. Now, in order to compensate for this, we could also scale this by 1 over 1 plus 2 delta. So, well, I will be with you in a minute. So, basically what will happen is the peak will become scaled to 1, and everything will fit together. Yeah.
Sir, what about the phase?
So, that is why I said I am taking a 0 phase response. So, when you take linear phase functions, you can write it as h naught of z as e power minus j omega n by 2 and then a amplitude term. So, I have taken off the e power minus j omega n by 2 and only working with the amplitude term, right. So, that is why easier to explain it in the context of a okay. Now, I want you to quickly follow along with me, because we have made the assumption of linear phase. I want to make a statement or just refresh your memory about the 0 locations of a linear phase filter. 0 locations. Because of the symmetry, h of z has the following form: h naught plus h1 z inverse plus h2 z minus 2 plus h1 z power minus n minus 1 plus h naught z power minus n. I am looking at the case where there is even symmetry. Okay. So, you can verify that this can be written as h of z can also be written as z power minus n h of z inverse. These are real coefficient. So, if I have a 0 h of z naught equal to 0, if this is true, this automatically implies h of z naught inverse also has to be equal to 0. Okay. This is because of the linear phase symmetry, because of the symmetry conditions. Now, from the polynomial having real coefficients, this also means that h of z naught conjugate must be equal to 0. There should be a conjugate 0, only then you will get real coefficients. So, that comes from the real coefficients part. So, this also coupled with symmetry will also say that z0 conjugate 1 over z0 conjugate is also a 0. So, what you find is that you get a quad of zeros. You will get, if z0 is a 0 and it has real coefficients and linear phase, then you should also have a 0 at z0 star, should have a z0 at 1 over z0 and 1 over z0 conjugate. This is something you already are familiar with. I just wanted to just refresh your memory on this particular result. So, if I were to plot the zeros of a linear phase polynomial or linear phase filter, they would look something of this type. Okay. I would have zeros which occur as quads. So, that means there is a 0 here at the conjugate location, at the reciprocal locations also. So, if this is z0, this is z0 conjugate, this is 1 over z0, this is 1 over z0 conjugate. So, you will get quads of this type. This is because of the symmetry. Then you may also get zeros on the unit circle. Because its real coefficients, its conjugate should also be present, and you can have zeros on the real axis, inside or outside does not matter, you can have zeros inside or outside, but its reciprocal must also be present. So, the reciprocal will also be on the real axis. Okay. This is what has to be the 0 configuration or 0 locations of a linear phase real coefficient transfer function. Of course, you could have multiple, instead of the one quad you could have 2 quads, you could have many zeros present, but basically you will have zeros of 3 types. A quad, you will have a pair which is on the real axis, and you will have a conjugate pair on the unit circle. Okay. Everyone's comfortable with this? You agree with that? This is how a linear. Now, when I take a linear phase of this type, that is what it will have. When I shift it up to get it to this form, 2 things happen. One is this G0 in E of j omega becomes strictly positive. G0 E of j omega becomes greater than or equal to 0, that is 1. So, therefore, it allows me to write it as something magnitude squared, that is a step 1. The second one, from a 0 observation, there will not be any more single zeros, they will have to be double zeros, because those zeros have merged. Okay? Now, this is very significant, very important for the following reason. Now, if this is my 0 configuration, what is my 0 configuration? I can have quads, I can have reciprocals on the real axis, and I can have double zeros on the unit circle. Now, look at this observation. If I now have something of this form G naught of z, can I factorize it of the form H naught of z times H naught tilde of z? Which means every 0 must either go to H of z or H tilde of z, and they must give you the same magnitude response. So, here is a choice of zeros for spectral factorization. I will take Z0, I will take Z0 conjugate, so that means so that the filter coefficients will be real. I can take the 0 inside the unit circle, I will take the blue one here and the blue one here. Okay. Now, what is left for H tilde? Everything that does not have a tick mark, and you will find that you actually are able to satisfy the para-conjugation property, where the zeros have to be in reciprocal conjugate locations. Okay. So, this also affirms that you can get something of the form H naught of z, H naught tilde of z. Okay. So, which also says that I can write G E of j omega, E of j omega as H naught E of j omega magnitude square. Okay?
Can you explain that step again?
Sure. So, any linear phase filter with the real coefficients will have the following. So, I will write it I will write it in this form. The zeros of any linear phase FIR with real coefficients. So, this is how the zeros will be distributed. They can occur as a quad, that means Z0, Z0 conjugate, Z0, Z0 conjugate, 1 over Z0 and 1 over Z0 conjugate. Okay. They can occur as a conjugate pair on the unit circle. They can occur as a conjugate pair on unit circle. Okay. So, that means Z1 conjugate with the condition that mod Z1 is equal to 1, it is on the unit circle. mod Z1 equal to 1, and the third combination that you can get is a reciprocal pair on the real axis, because this does not need to have conjugate, but the reciprocal has to be present in order for the linear phase symmetry to be satisfied. So, which means that you will get Z2 and 1 over Z2, where imaginary part of Z2 is equal to 0. Okay, you will get 3 sets of zeros. Now, this set can be factorized into 2 parts, which will one go to h naught of z, one go to h naught tilde of z, the reciprocals are present. This can also be factored into that form, but this cannot be factored into that form because you just have conjugate pairs, you do not have the reciprocal part present. The way you can get that to happen is if these zeros occurred as double zeros. So, then what can happen, you can take one from here and one from there, and then you basically you have the reciprocal also present. So, that is the important part of this discussion. Okay. So, when does these double zeros occur is when you actually have lifted the amplitude response so that there is no negative values. That also says that you can write it in the form h naught e of j omega squared, because now it is strictly greater than or equal to 0, and therefore, it also hangs together with the factorization that we are looking for. Okay, if this is all right, then we are ready to go back to this case, 2 channel case. Please refresh yourself with the configuration. Now, we are going to apply it one last time. X hat of z is equal to t of z x of z plus a of z times x of minus z. Okay, that is the input output relationship. I am going to enforce the aliasing cancellation constraint. Aliasing cancellation, f naught of z equal to h naught of minus z, f1 of z equal to minus h1 of minus z, minus h, wait, this is h1 and this is h naught, h1 and this is h naught. Okay. So, this will give me aliasing cancellation. Aliasing cancellation is done. So, what I am left with is the remainder of the transfer function x hat of z is 1/2 of h naught of z f naught of z plus h1 of z f1 of z times x of z. Aliasing has been removed, and I now have to deal with magnitude and phase distortion. Now, recall that we enforced a condition called the QMF constraint. The QMF constraint said that the 2 filters are related to each other, and you can apply the following constraint: h1 of z is equal to h naught of minus z. So, therefore, we got the transfer function t of z to be equal to 1/2 of h naught squared of z minus h1 squared of z, correct. We got this expression, and the time that we were working with linear phase, we said we would take a type 2 linear phase. Type 2 linear phase, type 2 linear phase means odd order even symmetry, that is the order is odd even symmetry, that is the type that we are working with, and we showed that we can rewrite this of the following form, where T e of j omega comes out to be 1/2 of magnitude h naught e of j omega magnitude squared plus h naught e of j omega minus pi magnitude squared. Okay. And if you recall, we even did a design where we would enforce this as one of the design criteria, objective function, and then got a pair of filters which were linear phase. So, therefore, phase distortion was removed and this one was almost equal to 1, not exactly equal to 1, but almost equal to 1. I am sorry? E power minus j omega n, you are right. Thank you. So, you should have, let me erase this and write it as e power minus j omega n divided by 2, correct, absolutely correct. So, phase distortion eliminated, but magnitude distortion minimized. I cannot say it is eliminated. Phase distortion eliminated, magnitude distortion is minimized. Okay? Minimized. If you now go back and recall, how did we design these filters? We said if H naught is a low pass, F naught must also be a low pass. H1 as a high pass, H naught is low pass, H1 should be a high pass, and F1 accordingly. Okay. So, here is where a very interesting alternate approach is emerging. Okay. Suppose H naught and H1 were a power complementary pair, that is what we want, right? H naught and H1 to be a power complementary pair. Suppose they were a power complementary pair, H naught of Z and H1 of Z are a power complementary pair. Okay. Then what would you get? You would actually get H naught E of j omega magnitude squared plus H1 E of j omega magnitude squared is equal to 1. Okay. Keep an eye on the right hand side, but look on the left. This can be written using the paraconjugate property in the following way: H naught tilde of Z H of Z plus H1 tilde of Z H1 of Z equal to 1. That is the power complementary property. But why did we get this? Why did we get the right hand side? Because we enforced a QMF constraint. QMF constraint said the frequency response of H1 must be similar to the H naught shifted. Okay. Can I ask if QMF will be satisfied if the following is satisfied? So, instead of imposing this constraint, this is QMF constraint, right? This is QMF constraint. Can I also impose it in the following way? H1 E of j omega magnitude squared must be equal to H naught E of j omega minus pi magnitude squared. That is also QMF. That is also what it says, right? It's the magnitude squares have to be shifted. Agree or don't agree? Yes, okay. We have to take care of the phase, but in terms of the filter itself, because see, ultimately what we are going to do is the shape and the phase all are going to get captured, but at least in principle the QMF constraint says that. So the QMF constraint can also be visualized in this form. The QMF, this can be written in the following way: H1 tilde of Z H1 of Z. Now the phase is going to be present, has to be satisfied with H naught tilde of Z H naught of Z. Okay. Okay. And wait, I made a mistake. Minus, there is a minus sign, sorry. H naught of minus Z H naught of minus Z. Previously the old QMF constraint was this option, H1 of Z equal to H naught of minus Z, correct? That was what you and it could have very well have been this one, right, because these two are the same magnitude response. It very well could have been this, but of course you must allow for a make it causal. So let us explore this option. See, the whole idea of research is, if you have made an assumption and you ended up in some point and you go back and re-look at it and say, why not try the other option, is it a possibility? So here is a option. Can I consider h1 of z to be equal to z power minus n times h naught tilde of minus z, okay, and just take it with a minus sign, because that will help simplify things. But see, this is for causality, this is for causality. The minus sign you can come back and fill later if you want, but you take it with the minus sign, so without loss of generality. So here is what it is. So we have said that h1 of z is equal to minus z power minus n h naught tilde of minus z, okay. So h1 of minus z, which is what we will need in the transfer function, will be minus of minus 1, sorry, let me just make sure I get this correct. H naught of minus z will be the minus 1 followed by minus z raised to the power of minus n h naught tilde of z, okay. So this can be written as minus 1 raised to the power n plus 1 z power minus n h naught tilde of z. So this is, we can consider this as equation A. So if the choice that we have made, h1 is not h naught of minus z, but with its paraconjugate, then let me call this as B, okay. Now substitute B in the expression for T of z. T of z is h naught of z times h1 of minus z minus h1 of z times h naught of minus z, okay. This is T of z. Substitute into this expression with a half. So I get 1 half h naught of z, h1 of minus z comes from B, it is minus 1 raised to the power n plus 1 z power minus n h naught tilde of z. There is a minus sign. h1 of z has got a minus 1 leading, z power minus n h naught tilde of minus z and h naught of minus z, okay. Just regroup the terms. Z power minus n comes out, divide by 2, there is a minus 1 raised to the power of n. So I am going to make the assumption that if n is odd, then I will get the following expression, n plus 1 will be even, I will get h naught of z, h naught tilde of z, minus and minus becomes a plus sign, z power minus n has come out, h naught tilde of minus z, h naught of minus z, h naught of minus z. Okay, this is T of z. Now, do you know any filter that will satisfy this to be equal to 1? If this is a spectral factor of a half band filter, right. So, what do I need? I need to design a half band filter, shift it up, spectral factorize it, and then use that in the QMF, in the 2 channel filter bank. Where does that come into play? It comes into play here. I did not take the conventional QMF choice, but I chose the paraconjugate of the QMF, then actually there is no phase distortion, there is no magnitude distortion either. So, this is what gives us perfect reconstruction. So, this is perfect reconstruction, perfect reconstruction. That is perfect reconstruction. Okay? But maybe there is a little nagging doubt, well, you assumed n is odd, right? I mean, that is arbitrary. What did we say? G naught has to be a half band filter. What is the order of a half band filter? It is even but not multiple of 4. If I do spectral factorization, what will it give me? It will give me an odd filter, odd order filter. So, everything hangs together, there is nothing which is fishy about this thing. So, the final part is H naught tilde H naught has to be G naught of Z. G naught of Z is H naught tilde of Z H naught of Z. If this we design it with a half band as a half band filter with the appropriate lifting such that G naught E of j omega is greater than or equal to 0, then we are guaranteed that the length of this order of this one will be 4j plus 2, H naught of Z then will have order 2j plus 1, which means that it is odd order, and therefore, what you will get is the correct condition required for perfect reconstruction. Okay, so just write it down one last time. You have a 2-channel case. We are going to impose aliasing cancellation just like before. F naught of Z is equal to H1 of minus Z, F1 of Z equal to minus H naught of minus Z. The only difference is that we are now going to do a new choice for the this is aliasing cancellation for the magnitude response. We are going to say H1 of Z equal to minus Z power minus n H naught of minus Z tilde paraconjugate. With this combination, you can guarantee that T of Z is going to be Z power minus n divided by 2 if H naught of Z H naught of Z is equal to G naught of Z, where G naught is a half band filter. Okay, and maybe one last time we will look at the design of the half band filter and the lifting and all of those things, but this is what assures you that x hat of n is equal to 1/2 of x of n minus n, just a delayed version with the scale factor which we can take care of, perfect reconstruction. Okay. So, the 2-channel case is now over. Well, it's think of now extending it to 3, 4 and arbitrary. It is non-trivial, but the 2-channel case at least there is some intuition that we could have followed and we could follow the way through. So, beyond 2-channel we more or less have to rely on the mathematics. There is no intuition that can, because the what cancellation happens, all of that has to be based on. So, we will now go back and when we look at the M channel case, we will now go back and just do the mathematical analysis of the 2-channel case, extend it to the M channel and say, okay, only under this condition we will be able to satisfy perfect reconstruction. Okay. So, the M channel case comes as a extension but not necessarily in terms of the insights that we got from the 2-channel case, but from the mathematical framework of the 2-channel case. We pick it up from there in the next class. I am also thinking of making a switch rather than doing the M-channel case at this point. Let's leave filter banks for some time. Let's go do OFDM, something a little different, gives you a different perspective. Once we finish OFDM, we'll come back and finish the M-channel case, because the M-channel case is somewhat mathematical. Let's focus on OFDM, which is a lot more intuitive. Thank you. We'll see you tomorrow.